Welcome back to ECE 501B. Homework number 1 is due today. I guess I'm starting early according to the wall clock. I was looking at my tablet clock. I apologize, but if you come in late, it won't upset me. Homework 2 is due in a week. This is Wednesday. We had a long weekend, and hopefully over that long weekend, maybe you were able to look at some additional material, in particular the last pieces of Chapter 2 that we are going to cover in a lecture format. And then today we will actually start linear maps, which is Chapter 3, and that's what you need to be studying, is Chapter 3. And I believe those 3 chapters will be the basis for exam number 1. The contents of Chapters 1, 2, and 3, that's what I'm envisioning you will be responsible for exam number 1, which is coming up sooner than you might think, but it's at the end of September on Wednesday, the 26th of September. Today what we want to do then is start talking about linear maps, and properties of linear maps are that it's somewhat like this idea that we've talked about with vector spaces. We need to make sure that these linear maps have an additivity and a homogeneity property to them in order for them to be a linear map. We'll give some examples. We'll even look at this abstract concept of a linear map that's actually creating a vector space from a set of linear maps. So we have these linear maps, and as long as they satisfy these properties of a vector space, that can be a vector space, the set of linear maps. Then we will talk about something that you've probably encountered before in a linear algebra class, and that's null space and range space. But we'll be talking about those in maybe more abstract ways in this class, but we'll generalize those ideas to where now they are associated with a linear map that is mapping between a vector space V and a vector space W. Here's the picture. We have one cloud going to another and transitioning between those clouds. Each cloud is representing a vector space, and now a linear map is a function that maps between those two vector spaces. So now I'm going to complete that sentence in terms of a linear map is a function that I'm calling or labeling as T in this diagram between, on the left, V, that's like the input space, and W is the output space, or the domain and the range. We'll call them many different things, but a linear map is a function that takes as its input an element, or maybe you want to think of this as what we've been calling it before, or also we've called it a vector. So now this map, this linear map, is a function that takes a vector of a, and this is maybe why it's better to call it an element so we don't have too many vector words floating around, but it takes an element of a vector space V and uniquely identifies an element. Again, that could be thought of as a vector in the output vector space, but it uniquely identifies an element of the vector space W. And instead of always writing this wordy description of a linear map, we have a shorthand. Many times we will simply write T such that V maps to W, where T is our map, and this is trying to represent that we're going from a vector space V to another vector space W. So we have this map T, and this map T can be more than just a matrix. But if you want something to sort of hang your hat on occasionally, you may just say, oh, a linear map, that's something like, or it can be thought of as a matrix. But it can be other more abstract concepts. But if we do have this linear map, it actually requires two properties. In order for it to qualify as a linear map. And those two properties are additivity and that's what you would think it would be. You take a vector U and a vector V, both from the domain vector space, capital V. You add them together, and those better give you the same result, or the same vector, as T operating on U plus T operating on V. That's the additivity property in order for it to be a linear map. It also needs to satisfy a second property, which we will call homogeneity. Where this is now, if we scale an arbitrary vector in our vector space V and pass that scaled vector through our map, then that better give us the scalar times the map applied to that original vector V. A is an element of F. There's our scalar, F being real or complex, and we need our vector to be in the input space, capital V, or vector space. We need then our map, if we want it to be a linear map, to have additivity and homogeneity. So together, these properties make a map linear. And I may get, my notation won't be unique. That's what this star is trying to indicate. I'm probably going to be guilty of mixing notation. Meaning I may say T parenthesis V, where V is the argument of this map, or I may just write it as TV. And it's T lowercase v. Don't be thinking about your television programs that you're going to go home and watch when I say TV. It's T as a map on this vector V. So I may say T of V, TV, and we'll say then that the script L, parenthesis, capital V, capital W, that's what we are going to define as the set of all linear maps T that take V to W. So if I say T is an element of script L of VW, now you know a little bit about T. It's living in, or it belongs to, this set of maps, linear maps, that go from V to W. And depending on what V and W are, that's obviously going to influence what T is, or what it can be. This linear map is extremely broad in terms of a concept. Linear map is an extremely broad category or idea. Let's look at some examples that are discussed in the book. And that means we're in chapter 3. So one of the first examples is the zero map. This actually maps all elements of our vector space V. Where would you expect those to get mapped to? The zero vector of your output vector space. So the zero map maps all elements of V to the additive identity in W. And we might write this then as OV equals O. And now O can mean all sorts of things, can't it? But what's it meaning on the left? Now this is going back to my TV notation, right? Without the brackets, we could say O open bracket V close bracket. What's this O trying to represent? This is now a map. Do you see the different continents and the oceans on that map? No, sorry. But you now have a map. It operates on V, and what does it produce over here? Is it a map? No, that's the additive identity, isn't it? In W. This is the zero vector. Whatever the zero vector means in W. So 0 is the additive identity in the output space W. And you've probably heard this many times, especially if you play with MATLAB, that certain properties are overloaded. I'm overloading 0 or O, or however you want to refer to it. This 0 notation is overloaded. And by overloaded, I mean that I'm using the same symbol. I'm sure somebody is going to say, well, why don't you put a bar over it, or why don't you bold it, but it's probably more convenient actually to just leave it as the same symbol, and then you understand by context what that represents. The same symbol means several things. That's what I'm meaning by overloaded. For example, if we go to our picture of what we have, here's V, and here's W. And now if we go through the 0 map, I could go here from, let's say, this vector v1. And where do I go if that's the zero map? If I now go mapping v2 through the zero map, where do I go? The same place. So now I'm mapping to here through the zero map, and maybe here's v sub 3. Through the zero map, I'm now going to 0, which is really just the zero vector in W. So here is our zero vector. What are these? Those are the maps, aren't they? So this is now representing the zero map, and these v sub i's, no matter what they are in V, go to 0 in W. That's the picture of the zero map, a linear map. What about the identity map? This maps each element in V into itself. So now if we have this identity map that belongs to this set of linear maps from V to W, then if we said IV, what's that going to produce? V. The identity map is a linear map. That's supposed to be a script L. Does that not look like a script L? What's it look like? I don't know. Don't turn me into my elementary school cursive teacher. Did you guys have classes in cursive writing? Probably not. Now you learned how to type in kindergarten, probably, huh? Or preschool. All right, zero map, linear map. We also have a linear map that could be the differentiation map. So let's say T is our differentiation map, and that's now an element of L. And let's be a little bit more descriptive in the arguments of this L. The input space, let's say, is the set of all polynomials all over the field of reals. That's what I'm meaning now by script P of R. That's our V. And if we now have polynomials that we're differentiating, what's the output vector space? Same. So it's now this script P of R. Or if we now have a vector, P of X, that's in R, for example, let's say that now P of X is equal to 3x squared plus 2x plus 7. What's TP? If we now apply this differentiation map to P, if we operate on P by T from calculus, what would you say the derivative of P of X is equal to? That's what we're doing. That's our linear operator. Differentiation is a linear map. This now becomes 6x plus 2. Or I might write that as T of P. Either way, I have the same result. So really, t of p is p prime, where the prime is the derivative of p with respect to x in this case. Does that actually satisfy the two properties of a linear map? And the two properties were additivity and homogeneity. And we can check that. Additivity. That says if we have t applied to, if we have this differentiation map applied to the sum of two polynomials, p and q, that's equivalent or equal to the derivative, the prime, of p plus q. But now you know what p plus q's derivative looks like in terms of p and q. Can it just be p prime plus q prime? The derivative works with that summation operation between p and q. But p prime, as we defined here, is what? That's tp. And what's q prime then? T of q. And isn't that what we want for additivity? T of p plus q is equal to T of p plus T of q. Additivity is true or holds for the differentiation. What about homogeneity? Now if we scale the polynomial by a scalar, what's that scalar look like relative to x? It's a constant. So now that can be factored out from our differentiation operation. But that now says that we have a T of p, and so yes, homogeneity is satisfied. That then demonstrates that the differentiation operation relative to polynomials is linear, a linear map. What about integration? And here actually we have two categories of integration. We have what? Do you remember what I'm trying to get you to think about for integration? Maybe erase the limits on the integral and keep them in another case. So we have indefinite integrals and we have definite integrals. And those actually correspond to two different v's and w's, so to speak. So if we looked at the indefinite integration, what would be in our vector space, input vector space? Let me tell you what I'm putting there. And now what's the output vector space for the indefinite integration? That's also a polynomial over the field of reals, isn't it? So this is now P of R. That would be our linear map. What about a definite integral? Where do we end up vector space wise with the output of a definite integral? Now it's real, isn't it? Do you see that it depends on what t is, what v and w will be, or vice versa? What's another example of a linear map? This one is called dimension changing, where now this linear map T is, let's say, going from R3 to R2. Or what would that look like? I'm kind of getting ahead of myself, but if you're trying to think of what in the world dimension changing, we'll write it a little bit differently right now, but if you're grappling with what that means, what would that look like maybe as a matrix? Can you see how you can change dimensions by matrix multiplication of a vector? Go from a 3 vector to a 2 vector in this case. What kind of a matrix dimensionally would we be using to make that happen? Is it a square matrix? Is it a 3 by 2? We want to have an input as a 3 vector, and we want our output to be a 2 vector. It's a 2 by 3, isn't it? Matrix. So now our matrix needs to be short and wide instead of tall and narrow. It's a 2 by 3. We need 2 rows, 3 columns to be compatible with an input matrix or an input vector that's 3 coordinates tall and 2 at the output coordinates tall. Here, what we will do is sometimes we will say OT of x, y, z. Those are our 3 components or coordinates of the 3 vector, is now going to produce 2 coordinates. And here's just an example. It might be 2x minus y plus 3z. That's the first coordinate, is a linear combination of the 3 coordinates in the input vector. And the second coordinate of our output going into R2, let's say, is 7x plus 5y minus 6z. Where this is now, let's say, W1, W2, and this combination is W. That's another linear map. Pardon? What has this? So the question was, they have the same dimension. What dimensions? So here, look at how many slots I have relative to the commas in my argument. T, I now have how many coordinates that T is operating on? 3. I have an x coordinate, a y coordinate, and a z coordinate. Now how many coordinates do I have in the result or in the output? Now that comma, I just have 1 comma, so I'm splitting it into 2 pieces. Now each of those pieces is a function, a linear combination of the 3 coordinates of my input vector. But this is now a linear map. From an input vector, x, y, z, to an output vector, w1 and w2. Where w1 and w2 are combinations of the 3 coordinates of my input vector. Is that clear? So now this is another way of writing that 2 by 3 matrix. We'll talk about how we represent a linear map with a matrix later, but for now, this is how we represent a dimension changing linear operator. Do you see how we could go the other way? We could go from smaller to bigger in terms of dimension of the vectors, a dimension changing in the other direction. All right, so now let's go to another linear map, a projection map. where now t starts in R3 and stays in R3, but will probably project onto a subspace in the R3 vector space. Question: is the projection map linear? Or maybe I should show you what I'm meaning. Now I'm saying suppose we have t of x, y, z, and the projection map that I'm considering here is xy0. So now think of a box that has an x side, a y side, and a z dimension. Find a point in that box, and now what are we doing? If x and y are on the bottom of that box, we're projecting that point to the xy plane, or the bottom of the box. Is that map linear? Well, if it's not clear, we can just do a direct proof, can't we? We can check additivity and homogeneity, and if it has those properties, then we can say, yes, that's a linear map. Let's then do a direct proof. To try to illustrate or verify or validate the answer to that question. So first, I didn't know that proof was so interesting or funny. Sorry, if you're listening to this, just assume that somebody in the other room is laughing. So maybe they are at your place of where you're watching this. Maybe at the next table they're watching a funny video and you're watching this video. Which one is more interesting? Don't answer that. Don't do a direct proof. Don't even do an empirical proof of that. But let's go on the direct proof of this. Okay? So now we want additivity to try to demonstrate that it satisfies that property. Suppose we let U be a 3 vector, U1, U2, U3, and let's let V be a 3 vector. And we haven't specified exactly what those are. We just said assume or take U and V. So those are arbitrarily removed or selected from the input vector space V. T of U plus V is now going to be T of U1 plus V1, U2 plus V2, and U3 plus V3. By definition of our projection map right here of Txyz equaling Ty0, what happens now to our result? How many coordinates do I have in the result? 2 or 3? 3. The third one is 0, isn't it? We're projecting, we're basically eliminating U3 plus V3, but the other two come through unchanged. But we can now think of that as U1, U2, 0 plus V1, V2, 0. But that's simply T of U1, U2, U3 plus t of v1, v2, v3, or tu plus tv. So it does satisfy additivity. And homogeneity, now we need a scalar, alpha. And it's arbitrary. We just say pick or let alpha be coming from F. Now we have T of alpha V is T, oh, let me make that a U. My V's don't look very good. Maybe my U's look a little bit better in terms of what I can draw. So now I have T of alpha U1, alpha U2, alpha U sub 3. That's what happens when we apply a scalar to a 3 vector. If we now push those through this linear map, or what we're assuming is a linear map T, this projection map, what happens? What do we end up with? Everything is preserved except for the third element, and it gets zeroed, doesn't it? Or the third coordinate. So now we have alpha U1, alpha U2, and 0. Or we can now say that that is alpha times U1, U2, 0. But that's the same as alpha T of U1, U2, U3. Or that's alpha T of U. We then have this projection map T that we've defined, satisfying additivity and homogeneity. So T is linear. Let's look at another map. We'll call this a translation map where T is going from R2 to R2. Bless you. And let's define that then to be 2 of T applied to a 2 vector, U1, U2, is now going to be U1 plus 1, U2 plus 2. And I'm sure you can finish what I'm wanting to say on the question. Is the translation map linear? And now I might say on an exam, prove or find a counterexample, or prove or disprove that this map is linear. And you're going, oh, I need to prove it. I need to prove it. And you start thinking about a proof. But sometimes what you might want to do is what? Look at a few examples and see if in fact those examples are living up to what you're trying to prove. If all of your first 5 examples are falling right in line with what you're wanting to prove, then you go, maybe I need to prove this. But if you can then find an example or be guided to find an example that's a counterexample through your first few examples, you might go, oh, now I don't have to prove it. I just found a counterexample to invalidate that proof or that statement. Here our statement is maybe the translation map is linear. And we want to either prove or disprove that. What would your guess be, or do you have a guess? Does U1 plus 1 and U2 plus 2, does that look linear? If you had to sketch y equal x plus 1, would you say that's linear? Yeah, you would say that's linear, wouldn't you? But now we have this slightly different twist on linear, don't we? Because now what do we need things to preserve? Additivity and homogeneity. So now we can actually find a pretty easy counterexample to this and show that it's not a linear map. So here is our counterexample. So before I scroll too far down, let me just say the answer is no. And our counterexample is, and now this is a nice check. You don't even have to go through that many checks to first try to see if this holds, then okay, I need to look at some more examples. But first you might say, is the additive identity mapped to itself in this map? So here is a check or a way of finding maybe a counterexample, and that is the additive identity which is the zero vector, whatever the zero vector represents or stands for, is the additive identity mapped into itself? What's the additive identity in R2? 0, 0, isn't it? So now we pick U1 equal to 0 and U2 equal to 0. We now are looking at 0, 0. If we apply this map to U1 equal to 0 and U2 equal to 0, what do we end up with in our coordinates? What's in the first coordinate? 1. What's in the second coordinate? 2. Is that equal to the 0 vector?
No.
So it doesn't satisfy homogeneity, does it? You could pick a vector, scale it by 0, and it's not going to be true here. So this particular counterexample allows us to see that it does not, this map does not satisfy homogeneity. Now, why should a linear map map the additive identity into itself? Let's try to explain that or see that or convince ourselves of, if we have a linear map, then it better map the 0 vector into the 0 vector in order for it to be a linear map. Let's see if we can explain that. Here's an explanation. For why a linear map should map the additive identity onto itself. What's the homogeneity property? That's T of alpha V is equal to alpha T of V. So if a map satisfies homogeneity, it needs to satisfy this. Now, what we can do So we can actually go back to chapter 1 and pull out a fact or a property where we now have a scalar times a vector. What would that give us? So now we have this overloaded 0 again. 0 times any vector gives you the 0 vector. And this is proposition 29 in chapter 1. So now we have a scalar, which is the 0 element, or the 0 is 0, scalar, times a vector, giving us the 0 vector. Now, in our justification or explanation for why the linear map needs to map the 0 vector into the 0 vector, let's pick this scalar to actually be 0. And V can be any element in the input space, vector space V. Or now we have T, 0 times V, what's the argument? Or what's, now if I say T of what? What's in that argument? Isn't that 0? So this, we're just applying proposition 129 with our argument. But what do we know now if we now sort of cover up this T of 0 and we say, oh, if this is a linear map, then it has to satisfy homogeneity. So cover up the T of 0. What's on this next side of the equal sign? By homogeneity, if our map T is satisfying homogeneity. So this next little piece is from the homogeneity property. T of alpha V is equal to alpha T of V. But now, what can we put on the right-hand side of 0 times a vector? Zero vector by proposition 129 again, right? So here is, again, Prop 129. And what's the overall result? Or what I'm wanting you to see, maybe, is focus now on this and that. What's the left? The arrow pointing to the left is pointing to what? What is the argument? That's the 0 vector. What's it pointing to on the right? So that's the 0 vector, and what's it saying? That the map T takes the 0 vector where? To the 0 vector. So now we are concluding, or trying to justify or explain, that if you place the 0 vector or operate on the 0 vector by a linear map, it better take you back to the 0 vector. So that's the homogeneity property that we used, in addition to using proposition 129 to justify that, oh, if our map doesn't take the zero vector into the zero vector, there's a counterexample for it not being a linear map. And you might go home tonight and try to identify that overloaded zero in the different locations. We've already shown what it is in two of the places. You don't even have to spend much time, do you? What's this one and what's this one? There the zero is representing a scalar, isn't it? So now we have 4 zeros, symbols, and they mean two different things. Two places they're scalars, two places they're the zero vector. I don't know why it's not wanting to operate, but bear with me. Now it's back. It woke up for whatever reason. You didn't know that I was trying to scroll with my finger, but I was getting a little bit frantic up here. Maybe you didn't see that. I need to be behind a screen. I felt like I was the zero vector there for a while. But now let's look at something else. Let's look at norms. What about norms? And linearity. Or what we're really maybe asking is the following: are norms linear maps? And this norm concept we'll dive into a little bit later in the class, but for now I will just define them and we'll see if in fact some of them or any of them are linear maps. So this norm, we'll discuss norms later. But for now, let's just define them and see what happens. So to do that, let's go ahead and pick a vector x. Let's say that it's x1, x2, x sub n, and each of those coordinates are coming from a field of either reals or complex numbers. Definitions for norms. The one norm. Norms are typically symboled with two vertical lines on either side of the vector or the variable. Here we're saying the one norm is x sub 1, and that's now we take the magnitude of x1 and what? Actually raise it to the first power. We take the magnitude of the second coordinate in the x vector and raise that to the first power. We keep going, x sub n raised to the 1, and we now take what? Well, we raise that whole sum to the 1 over 1, where the one norm is, I needed a different color. So I'll try to find a different color, and maybe it will or won't work. Let's see. There's the 1 location for the 1 norm. So if that's the 1 norm, what's the 2 norm? And this is the typical norm that you're used to thinking about. It's the Euclidean norm. Pythagorean theorem in 2-space, for example. Or it's the distance between two locations. Now if we have the norm of x, the 2 norm of x, we take the magnitude of x1, so that could be a negative number, it could be a complex number. We take its magnitude and we square it. We take the coordinate x2 and take its magnitude and square it. Sum all of these coordinates magnitude squared, and then what do we do with that sum? Take the square root. So there's the square root of x1 squared plus x2 squared in 2-space. So this you might see then as the square root of the sum from n equal 1 to n of x sub I squared. So there's a generalization of length, but all of these norms are what? Telling us the size of x, of our vector. Do you see how you would find the 3 norm? The 4 norm? Keep counting. I'll come back in 3 weeks and maybe you will have reached the infinity norm. Probably not, huh? So what's the infinity norm look like? There's the notation. X double bracket infinity. So if you actually sort of did a thought experiment and said, well, let me think this through. If I take the first coordinate, its magnitude, and I raise it to the infinite power, and I do that with all the coordinates, do you see what might float to the top of those coordinates when you raise those to really high powers? The magnitude. Which coordinate is going to become dominant or the biggest? Am I not making any sense? So if I have a 3 vector and I wanted the infinity norm of that 3 vector, what would that correspond to? It's the size of the 3 vector, size in quotes. If that 3 vector had elements of 1, minus 7, 2, what would the infinity norm be? Pardon? 7? I said minus 7, negative 7, and you're saying 7? Oh yeah, we're taking the absolute value, aren't we? Or the magnitude. So minus 7 and 7, 7 is the absolute value of minus 7. Yes, we're just looking for the maximum absolute magnitude of the coordinate. That's the infinity norm. Because if you think about it, the biggest coordinate in magnitude, when you raise it to the high power, that's the one that's going to dominate. And if you sort of invert that power by 1 over infinity, if you could do that, you're removing the powering operation, but you're keeping the largest element. So the infinity norm is really the max over I of xi. That's the infinity norm. So now you know all about norms. If I say, give me the 5 norm, you know how to compute it. If I say the 3 norm. But the general ones are the 1 norm, which is the sum of the absolute values. The 2 norm, sum of the squares square rooted. And then the infinity norm, that's an easy one to find, isn't it? Take the absolute value and you take the one that's the biggest. All right. Is the 2 norm linear? Well, let's use our process or notation. T now is really corresponding to the map that takes a vector x and generates this 2 norm. So we could, maybe it would be cleaner to say T of x. And we want to know now, this is the T is mapping from, well, I didn't say, did I? Or did I give you an example? Let's say that it's mapping from R3, so now little n is 3, to the reals. Is that okay? Now, yt equaling this 2 norm is or is not a linear map. Should I put anything in that blank? Not, or did you all hear the nothing that I said? It's actually not a linear map. So what does it require for us to do if we are trying to demonstrate that this is not a linear map? Do we have to prove that? We just need to come up with a counterexample, right? So let's find a counterexample. Or see if we can come up with a counterexample. We can actually show that, let's say x in 3 space, let's say it's now something that's easy to compute. X is 1 minus 1, 1, and let's say y is 1, 1 minus 1. And that's actually going to yield a result such that if we added x and y and found the 2 norm of their sum, that's not going to be the same as the 2 norm of x plus the 2 norm of y. What's x plus y? First coordinate, x plus y, 2. Second coordinate, third coordinate, 0. So now we're finding the 2 norm of a vector that has one non-zero coordinate, and it's 2. So now we take 2 squared plus 0 squared plus 0 squared and take the square root. We just get 2, don't we? So this now gives us the number 2. But what is the norm of x? The 2 norm, it matters what norm. Norms are a size, but here we're trying to show something about the 2 norm. What's the 2 norm of x? Now we have 1, 1, and 1, don't we, in terms of magnitudes. We square those. That's why I said these won't be too hard. 1 squared, minus 1 squared, 1 squared. That's 1, 1, 1. 3 square rooted. So this is now the square root of 3. What about the 2 norm of y? That's the same, isn't it? So now is 2 equal to 2 times the square root of 3? Is the square root of 3 1? Not quite, is it? So this is now showing that, what is that? Roughly 1.7 times 2, 3.4. Is that right? So 2 is not 3.4, is it? So this additivity is violated. So we've now convinced ourselves with a counterexample that the 2 norm as a map is not linear. So this process that takes a vector and finds its magnitude or its size is not linear. All right, now, is everybody wide awake, all buckled in, had enough caffeine, have your helmet on, safety-wise, safety glasses? Alert. This is now an abstract concept that we're talking about. We've been talking about linear maps and it seems pretty clean. But here let's talk about an abstract concept. And that is creating a linear map from the set of linear operators. So here an interesting development is that we can turn the set of linear maps script L of VW into a vector space. And the fact that we can do this is an example of an abstract space. Some of these linear maps are something as simple as a matrix. Now we're talking about linear maps that themselves form a vector space. So now we have a set of vectors. What are the vectors? Those are these linear maps, aren't they? So now we have a set of vectors, the elements of LVW, and what do we need? Well, and a set, let's say, of scalars and let's just keep those general. Those could be real or complex scalars. If we have vectors and scalars, for it to be a vector space, we need them to be satisfying what? Or we need two binary operations. We need to be able to add these vectors together, and we need to scale them. So we need two binary, let's say, functions or operations. where now we have vector addition and scalar multiplication. So let's say that we have a linear map S and a linear map T that are vectors in L of VW. Then we can define the vector addition S plus T to also belong to this set of linear maps, where S plus T operating, let's say, on V is equal to S operating on V plus T operating on V for all V's in our input vector space capital V. What is the small v? That is whatever this linear map, so it's now small v is coming from capital V. So the linear map, I'm sorry, these yes, we have this linear map S and T that are vectors, and now those operate on a V in our vector space capital V. Then we need, for scalar multiplication, we can have alpha coming from F and T belonging to our linear vector, coming from our set of linear maps, V and W. Then alpha T is also in the set of linear maps. Where alpha T applied to V is just going to be alpha scaling TV. With those definitions on these linear maps, they now form a vector space. Let me ask one question here. Now that you're all experts on these properties of linear maps, what is the additive identity of this newly created vector space L of VW? That's our zero map, isn't it? We need to take this additive identity needs to be such that you give me a vector, a linear map, I add the zero or the additive identity to it, and I get the linear map back. So that's going to be the zero map, isn't it? So now this answer to that question is, now we have the zero map, which again is this overloaded symbol 0. But that zero map now added to any linear map gives us back that any linear map. And that's what we need for it to be the additive identity. That's probably enough for today, huh? But be thinking about null spaces, which also correspond to zeros, and range spaces. And that's where we'll pick up next time in Chapter 3.